Okay, so welcome back to the second video on the NMDA receptor. Right, so in the previous video what we've seen is the structure of the NMDA receptor. We have seen that there are these 7 different genes which code for subunits of the NMDA receptor, and that they can form tetramers in the way shown by this diagram. And in every single heterotetramer that you make, and you can only make heterotetramers, you cannot make homotetramers in this case, so tetramer. In every single heterotetramer that you make, you have to have 2 gluN1s basically, and then you can have 2 other ones here basically, and they can either be the same 2 in these vacant 2 positions, or you can have different ones and you can form a heterotetramer out of 3 different subunits. Right, we then looked at the membrane spanning topology structure of each one of these subunits and how they have 4 membrane spanning subunits if you count M2, which is more a loop that doesn't quite manage to span the membrane, as a membrane spanning subunit. Right, okay, so now let's look at the actual function of these NMDA receptors. Right, so let's say we have the membrane here, and let's put one of these NMDA receptors in this membrane. Right, here we go. So what we know instantly is that 2 of these subunits are of this N1 type, and that actually is very important because the N1 subunit doesn't actually bind glutamate. It binds something different instead. So let's colour those N1 subunits in pink so that we keep this notation up here. So let's have these 2 here as being the N1 subunits. So this one here and the one behind it there. Those are both gluN1 subunits. Okay, so gluN1. Right. Then we can pick 2 others to go in here. And they can either be the same or they can be different, as long as, if they're going to be different, they are one of these 3 options here. Okay, so let's, for argument's sake, have them as the same. So let's do this one with glue N2D. So let's have 2 glue N2Ds in here to make us an NMDA receptor. Right, but it could have been any of the other 2, or any of the alternatives basically. So glue N2D. So both of these are glue N2Ds. Right, so to make the NMDA receptor adopt the active conformation in which the pore, which is down the middle of these 4 subunits, is open, then what you need to do is you need to have 2 glutamate molecules which are going to come and bind to the ligand binding domains of these 2 subunits here. So the 2 non-gluN1 subunits basically. So this is the same no matter what subunits you have in this position, i.e. whether they are a homo tetramer, whether you've chosen these 2 as being the same here, or whether they are different, i.e. in the case of this one here. Basically, 2 glutamates are always going to bind to the 2 non-gluN1s. Okay, so glutamate and a glutamate binds here. And both of these subunits here have this same membrane spanning topology, and the ligand binding domain is formed by this extracellular portion of the N-terminus here, just above the M1 membrane spanning alpha helix, and this extracellular portion here, just after the M3 membrane spanning alpha helix. Okay, so glutamate is going to bind to the ligand binding domain of these 2 subunits, and you're going to need 2 glutamate molecules, therefore, to come in here. Now, the gluN1 subunit is very special, and this is why you always have 2 gluN1 subunits in whatever NMDA receptor you are talking about. It does not bind glutamate at its ligand binding domain. Instead, it binds glycine. Okay, so glycine is a co-substrate for the NMDA receptor, basically. There's also another option. It doesn't necessarily have to be glycine. Instead, it can be D-serine. So glycine or D-serine has to bind to the ligand binding domain of GluM1, and you also need another molecule of glycine or D-serine to bind to the ligand binding domain of the second GluN1 subunit out of which the NMDA receptor is constructed. Okay, so to activate the NMDA receptor, you need 2 molecules of glutamate and 2 molecules of either glycine or D-serine, basically. So let's just discuss the structure of the amino acids glycine and D-serine. So glycine, the structure of glycine is, if we draw the basic structure of an amino acid here, here's the amino terminus of the amino group of the amino acid. Here's the carboxyl group coming down here. Okay, and then off the side you have the normal hydrogen, but in the case of glycine, glycine is the simplest possible amino acid. It has a hydrogen coming off this carbon as its R group. So that is glycine. Now for D-serine. Now D-serine refers to a specific enantiomer of serine. So let me just draw the basic structure of the amino acid here. COOH down there. Right, and then off here you have this group. You have a methylene group and then a hydroxyl group, and that basically is the structure of serine. Now what I need to try and explain is what the difference between what is D-serine, what is that referring to? Okay, so jump into the explanation of enantiomerism. Right, so if we to see how amino acids have 2 possible structures, how this serine has 2 possible structures, what we need to do is not draw the molecule like this in 2D. We need to, draw it in 3D, basically. So if we now try and draw it in 3D, then basically we'll put this central carbon, this alpha carbon of the amino acid, right in the center here. We'll also put the hydrogen, again in the plane of the piece of paper, going straight up from the carbon. Then what we'll do is we'll put the amino group back here, H2N. Again, that's in the plane of it's in the same plane as this piece of paper. So all of these molecules are in the plane of the piece of paper. Now, I'm going to draw one of these groups coming out of the piece of paper. So to draw a group coming out of the piece of paper, you use this sort of line where it gets thicker towards the end. So that denotes that it will be coming out at this sort of an angle like that from the piece of paper. Okay, so here I'll put the R group to denote this R group here, basically, of serine. And then going into the piece of paper, which you draw as a dashed line like that, I'll put the carboxyl group. Now, this molecule, though it has another enantiomer, there's another molecule that is very, very different from, well, it's not very, very different, it's made up of the same stuff, but it is different, and I'll show you that. So here's the carbon, and here's the hydrogen. Again, we'll keep this amino group in the page, so all of these are in the same plane as the piece of paper. But now what we do is we swap these 2 groups round. So going into the piece of paper, we have the R group, and coming out of the piece of paper, we have the carboxyl group. Now, basically, you cannot think of atomic bonds as being flexible things. I cannot just take a molecule that looks like this and just swap the R and the COOH round. The carboxyl group and the R group are fixed in their positions. This goes into the page and this comes out of the page. Without breaking this bond and breaking that bond, you cannot just swap them around as I have done in this piece of paper. So these 2 molecules are different molecules. You cannot turn this one into this one without undertaking a chemical reaction. And basically, if you look at them, it's not just that you can't change this one into that one just by changing the way you're looking at this. No rotation you do of yourself will change the way this looks. You can't just rotate this molecule around and hope that you can superimpose it on that, because look, if I want to try and superimpose this molecule on there, I take this forward, I take this carbon forward, I take this amine group forward, and now it's stuck. You can't move these groups, because once you've kept all those in their positions, these things are now stuck. And oh, what's this? This R group is sitting on top of this carboxyl group, and this carboxyl group is sitting on top of this R group. You cannot superimpose these two molecules. Try and appreciate that those are separate molecules that are different. Their structure is different, and they will potentially interact differently. Right, so that is what is meant by there being two optical isomers of serine. So these are optical isomers. Now, glycine is very simple. It does not have optical isomers. Now let me try and explain why. If the R group is another hydrogen, then there is a way of superimposing this structure onto that one. So let me draw this out as a separate little picture down here. So okay, now let's make this R group a hydrogen. So here's the amino group here, and then we've got this hydrogen now coming out of the page down here. So let me bring this up a bit. Here's this hydrogen coming out, and then going into the page we've got this carboxyl group. Okay, and we want to superimpose this onto, now let's draw out this one. You have the hydrogen going up there, an amino group coming down here, and then this carboxyl group coming out of the page, and then this R group going into the page, but that's now just a hydrogen. We can superimpose this onto this, and the way to do it is by doing a rotation. Basically, what you're going to do is you're going to rotate these ones around. You're going to keep the amino group in exactly the same position. So the amino group's going to go there. The carbon here is going to be kept in the same position, but you're now going to rotate all of these around. And you might say, but why are you allowed to do that? Well, okay, instead of rotating this, rotate yourself. Rotate your frame of reference, basically. Rotate your head, and this one I can make look like this one, basically. Okay, so if you rotate this around, like in this direction here, then what's going to happen is this carboxyl group here is going to come into this position. So that's perfect. That carboxyl group is going to come here, and then it will be superimposed on this carboxyl here. This hydrogen is going to come down to where the carboxyl group is, and that's then going to be superimposed on this hydrogen over here, so that's perfect. This hydrogen is going to go up to where this hydrogen is, and that's then going to be superimposed on that hydrogen. So I can turn this molecule into this molecule just by rotating my head. And okay, I've drawn it on the page as though I'm rotating the molecule, but if you prefer to think of it as rotating your head, it's more difficult to draw that. But I could just rotate this molecule around, basically, and then it will look identical to this one. So because you haven't got 4 different groups around the carbon, this is not a chiral center, and it doesn't give rise to 2 different enantiomers. So glycine is the only amino acid where there aren't 2 enantiomers, because you've got these 2 groups are exactly the same, so you don't have 4 different subgroups around that carbon, whereas in serine you do have 4 different groups. So it gives rise to these different enantiomers. Now, which is the D enantiomer and which is the L enantiomer? Basically, if you've got a larvorotatory, the D enantiomer of serine stands for dextrorotatory, and the L enantiomer stands for larvorotatory. And basically, the way to remember which of these two is the larvorotatory and the dextrorotatory is to draw them like this, and look for how do you read the word corn. So you need to read this word corn, and basically you use the carboxyl, the CO from the carboxyl group, the R of the R group, and then the N of the amino group to make this. So in this case, you go from COOH to R to N, and you go round in a clockwise direction. So imagine you are sitting up where this hydrogen is at the top here, looking down, trying to read this word corn. Your head will go in a clockwise direction. Okay, so if your head goes in a clockwise direction when you do that, then you are looking at the larvorotatory enantiomer. okay, or the larvo-rotatory amino acid. Now, in this case, when you're trying to read it, here's the CO, then here's the R, so you're going to go this way, and then here's the N, so your head is going to go anti-clockwise in this case. So again, if you're a little man sticking up at the where the hydrogen is and looking around trying to read this corn, then your head will move in the anti-clockwise direction, and then this enantiomer is the dextro-rotatory enantiomer, and it's to do with the way in which it interacts with light, by which where these names come from. So when we say D-serine, we mean this form of serine, where the R group you substitute in the CH, the methylene group, and the hydroxyl group where that R is, and this form of serine. And basically the NMDA receptor is specific to D-serine. L-serine doesn't work. It's got to be D-serine. So that shows you the importance of these two molecules actually having different chemical properties. Okay, right. So, go on to the other side. So, let's say now that our NMDA receptor has bound 2 molecules of glutamate and 2 molecules of D-serine. What then happens? So here is our NMDA receptor, and it has successfully bound its 2 glutamate receptors to these 2 subunits, the non-GLU-N1 subunits. So glutamate is bound here, 2 molecules of glutamate, 1 to each of these subunits, and then glycine or D-serine has bound to each of these GLU-N1 subunits over here. Okay, right. So let me just write that down. D-serine / glycine. Right, okay. So what happens next? Well, the channel changes conformation and adopts an open conformation that allows cations to move. And the NMDA receptors are permeable not just to monovalent cations such as sodium or potassium, but also to divalent cations such as calcium. So both sodium, potassium, and then calcium can move through these NMDA receptors. Okay, right. So what I now want to do is discuss the currents that will move through this channel as a function of voltage across the cell membrane, because this is where it differs hugely from the AMPA receptor. Okay, and this is physiologically important. So what we're going to do is plot the voltage difference from the extracellular compartment to the intracellular compartment. So that means the electrical potential in the intracellular compartment subtract the electrical potential in the extracellular compartment. If I have a little man measuring electrical potential in the extracellular compartment, and he then moves into the intracellular compartment, measures electrical potential again, how much would it have changed, basically? So if it gets, usually the resting membrane potential across cells is negative 65 millivolts. So this little man, when he moves into the intracellular compartment and measures the electrical potential, it will have gone down by 65 millivolts is what that means. So that's what we are working out. How much is it different when you move from extracellular to intracellular? So we'll have down here minus 65, which is resting membrane potential. Here is 0, and up here we'll have plus 65 millivolts. Right. Okay, and we're also going to plot against voltage. What we're going to plot is current, and what I mean by current is current from the intracellular compartment to the extracellular compartment. So current means how much charge is passing through this NMDA receptor per second. And we're talking about how much charge is moving from the intracellular to the extracellular compartment. Now you might be wondering, why are we measuring voltage from extracellular to intracellular and measuring current from intracellular to extracellular? Well, basically we do that so that the graph looks nice, so that we get some nice sort of linear relationship, so that when voltage is positive, current is also positive, rather than having some graph that we have to draw in these two quadrants. So everyone prefers, a graph that looks like just to draw a little picture, a graph that looks like that rather than a graph that looks like that. That's why we do this. Right, so current what that means is how much charge is moving through this NMDA receptor in a second. And basically it's going to count positive charge as a positive current, basically. So let's start off with positive electrical potential this time, plus 65 millivolts. So firstly, let's ask what would we expect to be true, and then what we will see is what is actually true, and we will try and find reasons why what we expect to be true isn't actually correct in this case. So in AMPA, if you watched my video on the AMPA receptor, you get exactly what you would expect, but in NMDA you don't, and there's a nice, beautiful reason why. Okay, so let's start off with plus 65 millivolts. So this intracellular compartment is now at a higher electrical potential than the extracellular compartment. If this little man moves from extracellular to intracellular, the electrical potential he measures in the intracellular compartment is plus 65 millivolts of the electrical potential he measures in the extracellular compartment. Okay, so what should we observe? What would we expect to observe? Well, if this NMDA receptor is permeable to monovalent and divalent cations, so positively charged particles. If this is more positive than the extracellular compartment, how would we expect positively charged particles to move? Well, they're going to want to get to the area of lower electrical potential, so we would expect them to be moving out of the cell. So, we would expect, therefore, to see a positive current from the intracellular compartment to the extracellular compartment. So we'd expect to see something maybe like that. Now, as we made the electrical potential across the membrane less positive, let's say maybe we went down to plus 20 millivolts, what we would expect to see is now that means the intracellular compartment is still positive, it's still greater, it's still at a higher electrical potential than the extracellular compartment by 20 millivolts, but it's now the difference between them is less. So we'd expect the driving force of positive charge out of the cell to have decreased somewhat. So we'd expect the current going out of the cell to have decreased. So maybe we'd expect it to go down. Okay, and then if we went to negative electrical potentials, maybe minus 65 millivolts, what we would expect then is the intracellular compartment the electrical potential in the intracellular compartment is lower than the electrical potential in the extracellular compartment by 65 millivolts. So we would expect positive charge to want to move into the intracellular compartment. So we would expect positive charge to be moving from the extracellular to the intracellular compartment. We'd expect current to be going in the opposite direction to the direction in which we are measuring current. Now that counts as basically a negative current out of the cell. So a current coming into the cell counts as a negative current going out of the cell. So we'd expect maybe a negative current. And overall what we'd expect is probably maybe some sort of positive straight line linear relationship like this. That is not what you observe. You observe that in the positive regions. You do observe that for positive electrical potentials, you do indeed observe a nice straight line graph. But in negative electrical potentials, things start going wrong. It originally starts off obeying this straight line, but then it falls down and does something like this, basically. So we need to try and explain that. What on earth is stopping positive charge from coming into the cell when the electrical potential difference across the cell membrane is too negative? Well, basically, what was found to be causing this was there are magnesium ions in the extracellular compartment of the cell. In the extracellular space. So outside the cell, there are magnesium ions, which are divalent cations. Okay, now, if the electrical potential difference across the cell membrane is negative, then that means that the electrical potential in the intracellular compartment is lower than the electrical potential in the extracellular compartment. That means positively charged particles are going to want to go into the intracellular compartment because they want to be at a lower electrical potential. So magnesium basically tries to get into the intracellular compartment. So it tries to come through this NMDA receptor, and basically what it manages to do is get stuck. This silly ion gets stuck in the NMDA receptor and then blocks the pore. So when you go to negative electrical potentials, what happens is that actually all the NMDA receptors get blocked by magnesium ions, which are trying to go through them, and that is what completely stops this current at lower and lower electrical potentials, that basically all the channels are getting blocked by magnesium. Now, at more positive electrical potentials, let's say when the cell membrane was at plus 20 millivolts, then that means the intracellular compartment is at a higher electrical potential than the extracellular compartment. That means that the magnesium ions, which are these divalent cations, are not going to want to go into the intracellular compartment. So basically they're going to be happy just sitting in the extracellular space. So they don't go into the NMDA receptors, and they don't get stuck, and they don't block the receptor. So that's why we observe this perfectly normal behavior at positive electrical potentials, and even at slightly negative electrical potentials. It's only when you get to higher negative electrical potentials that the driving force for the magnesium to try and go through this NMDA receptor gets high enough that you start observing a measurable blocking effect. So that's what happens basically. Magnesium goes into the pore, blocks it, and then current completely stops. And that happens when you go to when you try and open the NMDA receptor when the electrical potential difference across the membrane is too negative. Okay, so we'll leave it there for this video and continue our discussion of the NMDA receptor in the next video.